So the greater force is going to be up here. That's going to be the 306 newtons. And the lesser force is going to be here, 257 newtons. Okay, now we should be able to also do this backwards. So sometimes you'll have a problem where you're given this, the 306 newtons tension in number 2 and the 257 newtons tension in number 1, and you have to figure out what the tension is pulling them and in what direction to produce this line. Okay, so in that case, you do construct it with vectors. You say, okay, we have a horizontal force of 257. We have a vertical component, I shouldn't say force, I should say component of 306 newtons. And then you use your trig skills to figure out what this angle is and what this side is. So for the side, you use Pythagorean, 257 squared plus 306 squared. Take the square root of all that. So 257 x squared plus 306 x squared equals square root it. Comes out to be 399.6, which is pretty close to 400 as far as I'm concerned. So that's 400. And then you can use your trig skills. Tangent theta is a good one, is the opposite over the adjacent. So the tangent of this angle here is going to be 306 divided by 257. Tan theta equals 306 divided by 257. 306 divided by 257 equals, and then we're going to take the inverse tangent to that, and we get 50 degrees. There it is. Okay, so you should be able to do those both directions. Given the tension, you can find, given this one, you can find the tension in these two, and given the tension in these two, you can find that vector. Okay, that's a pretty straightforward one. I think the first two homework problems that you have are like that. Okay, now let's go to what's a little more complicated. It's not really more complicated, but seeing how it works is a little bit more complicated. Okay, so this is an example that's in your book. I believe this is on page 127. This is page 127. All right. Now, the way that the book does this, I think is excessively complicated. I will show you the basic idea of how it works, but the math gets pretty dense. And I personally think that there's an easier approach or an easier conceptual way to see your way to the answer. Okay, so the example that's in the book, the way they explain it is not the same as what I'm going to be explaining right now. Okay, calculator, there we go. Okay, so one way, and this is just analyzing the force in this cable here, sort of like we did in the problem that we just did. It amounts to the same approach. It's just kind of turned on its side. I'm going to talk you to that one, and then we'll work that way through it, and then I'll show you another way. Okay, so the first thing the situation here first, we've got a crane, and the crane has a wrecking ball, and the wrecking ball has a weight of 2,500 newtons. And there's a cable here attaching the ball to the gantry of the crane because we're going to let go of that and let the wrecking ball swing and hit the side of a building and knock it down. Okay, that's the goal here. So there's tension in this cable, which is holding up the ball, and there's tension in this cable, which is holding it to the side. And somehow the weight of the ball itself is being supported. Now, first we have to think about the physics of this before we start diving into the math, all right? So we have to think, well, what is the driving force that's running this whole thing? And our first inclination is to say, well, it's the weight of the ball, obviously, because that's what's being held up. But in this case, it's really not, okay? Because, yeah, the weight of the ball is acting downward, but that downward weight is not contributing to the tension in rope number 1 here, because rope number 1 is perfectly horizontal, and there's no component of that weight which is stretching that rope. Okay, and likewise, the horizontal rope is not driving this because the horizontal rope is doing nothing to support the weight. So it's actually the cable which is attached to the top of the crane which is driving this whole thing. The cable has a horizontal component, which is stretching string number one, and it has a vertical component, which is supporting the weight. Okay, so we can make a force diagram here, and this is the cable is going upward, and this is a 20-degree angle, 20 degrees. Obviously, I haven't drawn it to scale. That's not 20 degrees, but we're going to label it as 20 degrees. And the weight is pulling down, that's 2,500 newtons. And number one is pulling sideways with whatever force that it's pulling sideways. By the way, what we're trying to figure out is the tension in the horizontal rope and in this cable here. So we're given the weight is 2,500 newtons. We're trying to find the tension in one and the tension in two. Okay, so this is the free body diagram. This is the way it comes out. Now, again, we apply some of our physics knowledge to this, and we have to recognize that however hard that number one is pulling on the ball, that's how hard this cable is pulling on number one. Okay, so there's a component of the tension which is pulling against number one. So this is the same as number one here. And if I'd drawn it to scale, these would be the same length, but work with me. And then there's also a vertical component of the tension in the cable, which is supporting the weight. So the length of this one is the same as the force coming down, and the length of this one is the same as the force pulling sideways. So we have 20 degrees, and we know this is that the weight is 2,500 newtons. So we know that this support force, the vertical component of the tension, is also 2,500 newtons. Okay, because this vertical component has to be the same as this vertical component. And that's enough to get us going. All right, so this angle here is also 20 degrees. So I'm going to clean this up a little bit. We have a right triangle. This is 20 degrees. This is 2,500. And this is a right angle. And now we're going to figure out the length of these two sides. Okay, SOHCAHTOA is still our friend. So sine of 20 degrees is equal to the opposite, which is 2 over the hypotenuse. I'm sorry, I mislabeled that. This is 1. This is 2. So sine theta is the tension in 1 over the tension in 2. There's not much we can do with that right now because we don't know either one of them. Okay, but the cosine of 20 degrees is the adjacent, which is 2,500 divided by the hypotenuse, which is 2. Okay, get that where there's no glare. And so we're going to see 20 degrees, take the cosine. We're actually going to divide that into 2,500. I'm going to assume that your math chops are good enough. Let's try that again. 20 degrees cosine, 2,500. There we go, 2660. So number 2 here, 2660 newtons. Going off the edge of my clipboard there. Okay, and that brings us back to the first one because now we know a value for 2. So sine of 20 degrees is equal to 1 over 2660. So we can actually keep that same number if we want to, so we can be more precise in the next one. So we're going to multiply that by the sine of 20, and that equals 909. So 1 equals 909 newtons. Okay? So what we've got is that, this comes out to be 910 newtons or 909. This one comes out to be 2660 newtons. That's our answers. Now, the last step we do is we see if our answer is reasonable. And we have shown that this tension in this one is much greater than the tension in this one, and that kind of makes sense because this one is supporting the weight much more than this one is. Okay. Notice that the total force in this one, 2660, is not the same as 2500 plus 900. That's not how it works, because we have different things pulling against each other in different directions. So the numbers literally don't add up. We got to use the sines and cosines to make it work. Okay, now that's one way to do this. I will come back to, you know what, I'm going to do the other way right now. So this method here, this is kind of reflects what the book does. It's based on this idea that the horizontal component of the tension of the cable is the same as the tension in cable number one. So the tension to the right is equal to the tension to the left, and then we do the math to kind of figure out where that goes from there. Okay, now there's another way we can do this. We can do this as force vectors. So we know that there is a 2,500 Newton force acting down, 2,500 Newtons. We know that there is the tension of the cable going up. That's the main cable here, that this is number 2. We don't know what the magnitude of that force is, but we know that it is pulling in that direction because we know that this angle here is 20 degrees. Okay, that's 20 degrees. And we know that there's a tension pulling up in that direction of some magnitude. And we also know that there is a horizontal force going back to the left. That's tension number 1. Again, we don't know what the magnitude of that force is. We don't know how long that leg of the triangle is, but we know that it is horizontal, which makes this a right angle. And this is the key thing, we know that it's in equilibrium. We know that the net force is 0. So if the sum of these 3 vectors, the weight of the ball, the tension in the diagonal cable, and the tension in the horizontal rope, adds up to 0, that we do have a closed triangle. Okay, now you'll notice that this vector diagram that we made looks very similar to the one that we made in the other step, except that in this one, the directions of the actual force represent what's happening in the real world. Rope number 1 is pulling horizontally to the left. The cable is pulling up and to the right. And in this diagram, yeah, this is the cable that's pulling up and to the left, this is the horizontal rope, and this is the weight of the ball. So the vectors in this diagram represent reality better than this one does. Now, the math is the same, the arithmetic is the same, because we know this side and we know this angle, we do the same process to come to the same answer. But conceptually, I personally find this method a little bit easier because you can transfer the vectors to a diagram and then create a triangle and solve it. Okay. The insight you need for this one is that it will form a closed triangle because the net force is 0. Okay. Let's go on to another one here. Let's see. Yeah, that'll do for now. And we will stop this one.